Okay, hi everybody. So today what we're going to do is we're going to talk about something called photoelectron spectroscopy, and then we're going to relate that to trends that we observe on the periodic table. So really from this you guys should understand how photoelectron spectroscopy is used to justify periodic trends. Okay, so first off, photoelectron spectroscopy, it's PES for short. Okay, and so what happens during photoelectron spectroscopy is electrons are stripped away from the atom one at a time. Okay, usually they use X-rays to produce photons of energy that are absorbed by the electrons. That in turn gives the electron energy to move away from the atom. So basically, photons bombard electrons and then knock them off of the atom. The energy necessary to remove each electron is measured, and that is known as ionization energy. Now we've talked about ionization energy before, and usually we look at, how much energy does it take to remove one of the valence electrons, or two of the valence electrons. But during photoelectron spectroscopy, we pull off all of the electrons and we figure out how much energy it takes to remove each electron successively. Okay, so one after the other, how much energy does it take if we just keep pulling electrons off of there? And so you'll notice that you end up with a graph that looks kind of like this. Okay, so be really careful when looking at the x-axis. Okay, sometimes it's labeled like we normally label, with the lower value over here on the left and the higher value to the right, so it increases in that direction. But a lot of time you'll notice that the x-axis is actually flipped around the other way. So you'll notice that the larger value is close to y, close to the origin, and then it actually decreases going out that way. Then the y-axis itself is what we call photoelectron intensity. Okay, and so what that is these peaks here, you can think of that representing the number of electrons. Okay, so these peaks here are relative to each other. If we notice this peak here and this peak here, they're the same size, so that represents the same number of electrons. And then this peak right here is 3 times higher, so this would represent 3 times the number of electrons that these smaller peaks do. Okay, so it's relative. Okay, so thinking about Coulomb's law, the attraction between electrons and protons, aka the nucleus, right, because that's where they're at, depends on the number of protons. So what is that effective nuclear charge? Okay, and it depends on the distance of the electrons from the nucleus. So we've been talking a lot about that this week. Okay, those two factors, number of protons, aka charge, and distance, affect the attraction between the electrons and the nucleus. Okay, if we increase the number of protons, then that attraction is stronger. If we increase the distance, that attraction is actually less. Okay, and you can think of Coulomb's law kind of like the kitchen magnet law. Opposites attract. The bigger the magnet, the more the force of attraction, and the further you hold them away from each other, the less you feel that force of attraction between the two magnets. Okay, the electrons closest to the nucleus are the most attracted to the nucleus and require the most energy to remove. So that 1s sublevel, the one that's the closest to the nucleus always, that is going to be the peak with the highest ionization energy. Okay, highest ionization energy. So if I look back at that graph that was on the front, if I look at the x-axis, this one increases left to right. So this peak right here is actually the peak with the greatest ionization energy. And so this peak right here must represent the 1s sublevel. Okay? Now we know that the 1s sublevel holds 2 electrons. And since there's a peak after that, I guess this sublevel must be full. So this is 1s with 2 electrons right here. So then the next sublevel to fill up would be the 2s sublevel. And that, since the peaks are the same height, there must also be 2 electrons there in that sublevel. And if you'll notice, that peak on the x-axis actually does not take as much energy, right? And that's because the 2s sublevel is further from the nucleus. Again, there's less Coulombic attraction. So it's a lot easier to remove the 2s electrons. It requires less energy than it does to remove the 1s electrons. Okay? And then after the 2s fills up, there's the 2p. And since this peak is 3 times the height of these peaks, I guess it contains 3 times the number of electrons. And so if these each have 2, then this must have 2, 4, 6. And so by looking at this photoelectron spectroscopy graph, we can actually write an electron configuration. The 1s sublevel is always going to be the peak with the greatest intensity, the greatest ionization energy. So you just start at the highest x value, you call that the 1s peak, and you go from there, okay? Okay, so elements with more protons require more energy to remove electrons. So if we were to compare 2 elements like hydrogen and helium, they would both have a 1s peak. Okay, they would both have electrons on the 1s sublevel. But the 1s peak for helium would be at a higher energy value than the 1s peak for hydrogen. Okay? And so if we were to look back at the graph that we just drew, right here, okay? If I think about this element, 1s2, 2s2, 2p6, I could actually find that on the periodic table. This is going to be element number 10. This is going to be neon. If I were to draw the same graph for another element, let's say argon, okay? If I were going to draw this for argon, the 1s peak would not be at the same place. Argon has 18 protons. Neon only has 10. So there's a greater Coulombic attraction between the 18 protons in argon's nucleus and the 1s sublevel than the 10 protons in neon's nucleus and the 1s sublevel. So if I were to draw peaks for argon, it may even go off the graph, but the 1s peak would definitely have a higher x value for argon. The 2s would have a higher value. The 2p would have a higher value. Then there would be a 3s, right? And then there would be a 3p. So that would be argons, and that would be neons. And even though they have partially the same electron configuration, I mean, they both fill up the first and second energy level, all of the peaks for argon would have higher x values. They would be over, you know, with higher x values on the graph because argon has more protons in its nucleus, okay? And so right here on this page, this is just another way you might see a PES drawn. And so instead of having it all on a single x-axis, they may break it up. And so again, this would be neon. If I look at these lines, this one goes from 0 to 10, this one goes from 10 to 100, and this one goes from 100 to 500. So the scales are different. So sometimes they break it up because the scales change. But if this is the greatest value, right, if this is the highest ionization energy, then this must be my 1s peak. So then this is my 2s2 peak, and this is my 2p6 peak. And this is still going to be neon, okay? Okay. So thinking about Coulomb's law again, attraction depends on the number of protons and distance. Okay, those two things play a big part in what it is we're talking about, okay? So the 1s electrons on argon, which again is number 18, are more difficult to remove, meaning that they require more energy, right, than the 1s electron on neon. And so we've already added that to our picture of photoelectron spectroscopy, okay? We already added that to our graph. We can see that all of the values for argon are higher than the values for neon. Okay, except for the electrons on the third energy level. Neon does not have electrons on the third energy level, but argon does, and they're actually easier to remove because they're further from the nucleus than the second level electrons for neon. Okay, so as we add levels, as we go further and further away from the nucleus, we can see that the ionization energy of those electrons decreases. Okay, and so there's a pattern there, right? If we increase ionization energy every time we add protons, then we can see a pattern as we go from left to right across the periodic table, okay? In the first ionization energy, which is energy required to remove a valence electron, okay, we can see that as we go across the periodic table, that's going to increase because the number of protons is going up, right? That's increasing. And so that attraction of the valence electron to the nucleus is increasing, and it becomes more and more difficult to remove them. It requires more energy, okay? Now, as we go down a group, it decreases because the distance is going up. As we add energy levels and those electrons go further and further from the nucleus, then it becomes easier and easier to pull them off. It requires less energy to ionize, okay? All right, electronegativity is the ability to attract electrons, so the ability to become a negative ion. And again, since Coulombic attraction increases left to right because the proton number is increasing left to right, this value also increases. But because the distance between the nucleus and the outer shell is increasing, and because those inner levels of electrons are kind of shielding the nucleus and preventing it from really having too much nuclear charge, this actually decreases as we go down a group. Okay. Electronegativity can be measured by calculating effective nuclear charge. Okay, so ENC is your effective nuclear charge, and so that's going to be your nuclear charge, your number of protons, minus your non-valence electrons, so aka your inner electrons, your core electrons, if you will, okay? So you take the number of protons and subtract all of the electrons that are not valence electrons, and that leaves you with your effective nuclear charge. The greater that is, the more electronegative that element is going to be, okay? Except for the noble gases, of course, because those have a full valence shell, and they're not going to gain any more electrons. That would be the only kind of exception to that rule. But the greater the effective nuclear charge, generally, the greater the electronegativity, okay? And then atomic radius, of course, is the size of the atom. And as we go across the periodic table and that Coulombic attraction increases, because again, the proton number is going up, that's going to pull electrons in, and so atomic radius actually decreases going in this direction. But because the number of energy levels increases as we go down. Like the first period on the periodic table, those elements have 1 energy level. Second period, they have 2 energy levels. Third period, they have 3 energy levels, so on and so forth. Because we keep adding energy levels, the atomic radius actually increases as we go down a group. And again, we actually see these trends verified by photoelectron spectroscopy. Again, looking at our graphs, we can see that the greater the Coulombic attraction, the greater the ionization energy is. And so that kind of verifies, this kind of scientifically verifies for us all of those trends that we've observed on the periodic table.